Hi there. So I've got more slides than time, and as a result, I would like to figure out what you people want to hear. So if I can do a quick survey, how many of you use Python or are comfortable with it? So most of you, okay. How many of you do embedded development? Most of you, excellent. How many of you would be interested in how to build your own image of MicroPython, to save space and make things fast? Okay, we got a couple there. How many people have used MicroPython or CircuitPython? Either one. Okay. All right. So I can get pretty deep into the weeds here if you're interested. You feel free to stop me and ask questions, but I'm going to have to clip through these pretty fast. If you want me to go back to a slide or whatever, feel free to do that. Okay, I assume everybody's here. Okay. So, who am I? I have been working with microcontrollers since the first one, the Fairchild F8, back in 1975. I've done embedded stuff and other things. Over the last 15 years, I've been doing product development for a contract programming development company, product development company. And so we've been constrained budget and schedule. Everything has to be in a hurry. I've got the object-oriented bug in the late 80s, started using C++, and then later Smalltalk. And it was because of that I got hired by Alan Kay and his group, who of course coined the term object-oriented. Worked with him for about 3 years, and have been watching the microcontrollers get bigger and bigger and faster and faster. And so through the years, I was certain that at some point we'd be able to run garbage-collected, dynamic, object-oriented languages on micros, and the time has been there for several years now. What I want to cover here is a little bit about MicroPython, although given your familiarity, I don't have to go too deep into that. An overview of how it works internally, look at a couple of my hardware projects that use MicroPython, development and debugging, and then the different levels at which you can build a MicroPython-based system, starting at the very simplest, where you're typing it at the REPL, all the way to building custom images, possibly with your own C code modules and so on, and then get into multitasking of sorts, async I/O and so on, and then optimization techniques. So MicroPython, you probably know something about this. It's been around for 10 years now. It is actively developed. There's a very supportive community. The rate at which pull requests get actually handled in the MicroPython lib, the libraries, is kind of slow, but MicroPython itself is pretty active, and they're pretty responsive to pull requests. MicroPython comes with, of course, a number of tools. Its own its build system is responsible for a lot of the cleverness and a lot of the savings that happen. Why would you use MicroPython? Well, one of the things, especially if you're doing this for a living, that people want to see, especially if you're dealing with startups, is they want to get something running fast, and they want to experiment, do proofs of concept, show things to investors, and so on. And the faster you can get something running, the faster you can decide if that something is actually something you want. But it doesn't have to stop at just doing prototypes, proofs of concepts. I'm actually shipping two products. That use MicroPython because both of them had compressed schedules. They will do over-the-air updates, custom images, and so on. Don't have to read microcontroller data sheets. MicroPython is reasonably portable. Reasonably portable between different microcontrollers. It has a REPL, read, evaluate, print loop, and so you can type things immediately. One of the things that I loved about Smalltalk was the availability of a REPL. Because it's Python and because you can compile a host MicroPython, you can do unit tests on the host, and at least for the parts that don't have to touch the hardware. And there's also a QEMU port, so you can actually do your CI/CD pipeline using QEMU to test on a simulated machine. Why would you maybe not want to use MicroPython? It's lower speed because it's mostly bytecode interpreted, although you can do things to speed up individual parts of the code. It does use a little bit more flash and RAM. The flash consumption, as your program gets bigger, the compactness of the bytecode begins to make up for the additional size of the actual interpreter. There's no interactive debugger. However, there are lots of ways of debugging in embedded systems, everything from wiggling pins, flashing LEDs, print statements, logging, and so on. If you need to integrate with C or C++ libraries, that requires either additional C code or FFI, something like that. And if you're more experienced in some other language, then Python has a small learning curve, but it's not too bad. There's a number of different ports. In MicroPython terminology, a port is an MCU family, whereas a board is a specific implementation of a microcontroller on a board with particular peripherals. So for instance, you can have pins that are named in the build. You can have specific on-chip hardware. If you've got an LED or something, you can support that. And of course, you can choose what goes into the build as far as libraries and so on. I'll be talking about a project that used a tiny Pico. So the port is the ESP32, but the board is the tiny Pico board. These are the major ports, the ones that are actually maintained heavily. ESP32 across a wide variety of chips. The ESP32C6, which a number of you may have gotten, is just waiting to be merged. But I did a build last night, and it seems to be working okay. I haven't tested the whole thing, but people seem to be happy with it. The MIMX RT is the i.MX RT series, including the Teensy and the dev boards. The NRF semiconductor boards, including the microbit, although it doesn't have much memory. Renesas RA, the Raspberry Pi 2040, which has got some exciting support for the PIO and DMA. SAMD STM32 is the biggest, and the original port Damien George did for the Pi board. And now there's a Zephyr port, although it's not really too widely featured, too heavily featured. And then there's some other special purpose ports. Embed, if you wanted to use MicroPython as an interpreter in, let's say, a game or something. Minimal, the QEMU port that I mentioned earlier is good for testing. Unix and Windows for your host testing, and a WebAssembly port, which I haven't played with at all. Can you all hear me okay? Okay. I'm sorry about all the words on the screen here, but CircuitPython also exists. It's got a different audience. It's really aimed at being able to educate people and to get them started quickly. I'm not going to get too heavily into this, but they've avoided some of the things like interrupts and threading that seem to get people in trouble. And it also presents as a USB mass storage device, typically on ports that support USB. So what goes into a typical MicroPython system? You may have a vendor bootloader. You may have a vendor bootloader, like on the RP2040. The ESP32 has a built-in loader as well. The MicroPython runtime itself, which is written in C. The QSTR table, they do some clever string interning, so strings that are less than 10 characters in length. There's only one copy of them, and they're immediate objects. So instead of having a pointer to allocated memory, it's just an index into a table, which saves a whole lot of space and allows you to not have redundant allocations. Then frozen Python modules. These are bytecode modules that get compiled into the Flash image and run from Flash. And then typically there's also a file system, which is the remainder of the Flash. You might have additional partitions, like on the ESP32, it's pretty easy to have over-the-air partitions, so additional Flash partitions. And then the RAM itself, if you compile something from Python on the device, then it ends up in RAM as bytecode. If you're, likewise, any short strings end up in additional string pools. You have free heap and stack. The default syspath includes .frozen, which is basically just points to a, if you will, a pseudo directory that has those frozen modules in it. So, any questions so far? Okay. So I talk about string and turning. There's fancy build stuff and macro magic that happen to do this. I'm not going to get too heavily into it, but it's responsible for a lot of the savings. STM32 port. There's a number of STM32s that are supported. ESP32 port, which I've been playing with quite a bit recently, basically runs as a single free RTOS task. If you make Python threads, they end up as additional free RTOS tasks along with the necessity of having stack and everything for them. It supports a wide variety of ESP32s, and it's built on top of the ESP IDF. I don't have to get too deeply into this, but those devices that have USB, native USB, just appear as a USB virtual COM port. There's good support for things like RMT if you want to run fast bit streams, one-wire cap touch, waking from cap touch, DAC available on a couple of them. The RP2040 port has got, again, it's a Cortex M0 dual core. There's no global interpreter lock, so you can have one thread on each CPU and get interesting interference between them if you work at it. So when we start up in MicroPython, and this is different than CircuitPython, the main.c or the main task in the free RTOS ports basically set things up, maybe certainly initialize the REPL, the main COM port, run _boot from frozen code, which mounts, possibly creates a file system if necessary. And then from the file system, if a boot.py exists, or if there's a frozen boot, it runs first, and then the main runs. And then at the end of main, you fall into the REPL with whatever globals came from the boot and the main still in your environment, unlike CircuitPython. So cross-compilation, we have basically the same compiler that's able to run on the host as runs on the device. So it's called MPY cross, and it's the way we get frozen modules is we run this to make bytecode .mpy files, and then those can get concatenated and burned into the image. Or you could just take the .mpy files themselves, copy them to the file system, and run them from RAM. Somebody ask a question? Oh, okay. Hearing noise out there. A couple of projects I've worked on recently. A cat litter box monitor. Figured ammonia sensor and a weight sensor, and do something with the data. This is working. I haven't gotten the data. I just finished it. But basically, I'm using a tiny Pico ESP32 and a load cell A to D and an ammonia sensor, and went to Goodwill on a Monday and got a bathroom scale for $1.99 and stuck it all together. So there's the hardware, and then I'm using an off-the-shelf library, MicroPython MQTT, and running some servers in Docker on my Synology device. So, and the other is a little board that I designed that goes in the vintage Fluke 5.5-digit multimeters from the 1980s. The one thing they lack is a continuity buzzer. and that really annoys me because that's one of the things I use the most on my multimeter. So I made a little RP2040. This is basically an Raspberry Pi Pico on the bottom there, and it interfaces to the 30-volt vacuum fluorescent segment data and interprets that. And it's only about 300 lines of code. So we can start out at the simplest, actually just typing things at the REPL. We type in an expression, a command, it runs it, gives us the result. So if you want to, for instance, do an I2C scan of the I2C bus, it's 2 lines of code, which you can type in. The REPL is always there unless you tell it not to compile in. If you're shipping a product, you might want to turn off the REPL and the compiler, for instance, if you don't want people messing with it. Network-enabled ports, there's a WebSocket-based web REPL, so you can get to it over the network. It's the same appearance as talking to it on the UART. And I use UPySH to do file system actions. There's several different Python IDEs. One I use sometimes, especially in teaching people, is Thani. And it knows enough to be able to program boards and to load modules, load library modules from the MicroPython library. So it's pretty handy. And then MP Remote comes with MicroPython. It's a command line tool, and it offers both file system actions, copying, making directories, and so on. You can get to the REPL. It's a serial terminal. And it also has the ability to actually mount a directory as /remote on your device. So you don't even have to copy files over when you're doing development. You can just have them on your computer, mount them, and actually just run them from that pseudo file system that appears as /remote, which is very handy. But if you want to be able to unplug that from your computer and run it, you'll have to get your code over to the device somehow. And initially, what I usually do is just copy .py files over. If I'm using library files that have already been debugged, I'll use the .mpy, the pre-compiled ones, and stick them in the /lib directory. And then, of course, you can edit the sys path to, for instance, allow you to override a frozen module with another one later. To add third-party libraries to the file system, we have MicroPython's version of pip called MIP. It's available either on the host or as a library that you can run on the device. And it's just a quick way of getting packages into your image. Here's a number of third-party libraries. I won't get into this because of time, but these are some that I use. These slides are going to be available on the Crowd Supply site. Freezing modules. As I mentioned, MPY cross is the cross compiler. It's the same as the compiler in the device itself. We use it to both produce the image and to produce distributions for library files as well. There's a manifest.py file. When you're building an image for a board, you can specify what libraries and what files will end up being frozen into the image. And that's all done in the manifest.py. You can, for instance, when I did my Catbox monitor, I already had a board definition that worked for this particular board, but I didn't. But I wanted to use additional files and different files than the stock image had in it, frozen. So basically, I just provided my own manifest.py. And so here's kind of a picture of the different ways we can get Python code into our system. Down here we have the PC taking a Python file, making a .mpy, and either freezing it as part of the build, or copying, or you can then copy them to the file system. When you run those from the file system, we have to copy them into RAM to execute them. Right now, there's no execution directly from the file system. If you have .py files on the device, you can use the on-device compiler, and that makes a .mpy, which again gets run from RAM. these are the major verbs that are in manifest.py files. You can include other manifests. You can have groups of files added, or you could put individual files in. How do we debug? Well, there's obviously print statements. That works. We can blink LEDs. We can wiggle pins, especially for timing analysis. That's very helpful. One of the things I do is I will take any part of my code that doesn't have to touch the hardware directly, and I will make unit tests for that I can run on the host using the host MicroPython. So the language is going to be the same, with the exception of the machine module, which has the actual MCU specific stuff in it. So I can actually run a limited version or a full version if I want of unit test, and check out my Python program logic. Also, you can say you could print out to a separate UART, so you'd still have your REPL and you wouldn't see your diagnostics coming out there. Or you can use logging, and I have a version of the MicroPython live logging module that works somewhat better. If you're making your own hardware that's enough different from one of the stock board definitions, or need different partition layouts and so on, you basically make a board directory, and you can put that in your own code tree. And there's a number of macros that allow you to enable, disable, or configure different features in MicroPython. For instance, that's where you turn off the compiler if you needed to. That's where you turn on or off USB or Bluetooth or networking or a variety of other things. ESP32 has an additional CSV file which just basically tells the build system how to build the partition map. The manifest.py and then pins.csv allows you to have human readable, logically named pins available in your machine.pin class. There are examples. MicroPython has pretty good documentation and a number of examples for various different features that are pretty good in general. It also has a section on let's say, making your own C modules, on manifests and so on. So it's not very frightening to actually get involved in development on. You can make an extension module, which would be a module that you would compile as part of the image build that ends up getting linked into, at build time, getting linked into your image. Typically you'd build those out of tree. Again, there's examples of those. You just basically add the files, and you're basically making Python in C. So there's an API that allows you to create objects and interpret objects and call functions and make functions that can be called and so on. You can also have native code in .mpy files, and this is a little bit more involved. There's a good talk by Matt Trentini in PyCom AU some years ago on YouTube. Again, there's examples and documentation on this, but it allows you to have dynamically loadable modules that are written in C or C++. Or I assume somebody could do this in Rust too, but I wouldn't want to try. You have to use position-independent code. There's linker limitations and so on, but it is possible to do that. This is kind of deep into the weeds, but a MicroPython object is either an immediate, things like small integers are immediates, or it's a pointer to typically allocated memory. The standard representation does not have floats as a native, as an immediate object, but there are two representations that do. One has there's the details of that. Remember I mentioned the QSTRs. So short strings are immediates, small integers are immediates. In some of these representations, floats are also immediates, and things like none and true and false are also immediates. How do we do multitasking? Well, there's interrupts. Depending on the port and depending on the interrupt source, typically we can have either hard or soft interrupts come in. These are callbacks into Python code that happen upon events. A hard interrupt is actually called in the context of the interrupt handler. So for instance, on the STM32 pin change interrupts, you can choose to have a hard interrupt. That's less latency, but more restrictions as far as what you can do in the handler. You can't allocate memory, which means you can't necessarily use a float unless you're using an object representation that's got floats in it as immediates. Soft interrupts do whatever work they have to do in hardware and then schedule a callback. And then the scheduled callbacks and exceptions get checked between the execution of individual byte codes. So it's a little bit safer, and you can do memory allocation and so on in soft interrupt handlers. So there's a variety of interrupts that are available, and often you can choose between hard and soft. You can have atomic sections with disable and enable. Yeah?
So, for the difference between hard and soft interrupts, what is the sort of worst case length of a byte code?
It depends on whether or not you have to wait for garbage collection. So one of the things you can do is periodically schedule garbage collection. But typically you're looking at like a millisecond or so for a soft interrupt latency. So if you need faster than that, consider hard interrupt, or consider doing your interrupt handling in C in a
So if you care about jitter, you probably want to.
if you care about what?
Jitter, for example.
Yeah, well, either that or you use a peripheral that doesn't have jitter, like the RP2 PIO or the RMT on the ESP32 gives you the ability to have very smooth bit streams. But again, keep handlers as short and simple as possible. This is standard embedded stuff. We do have threading available. I don't recommend it. There's a couple of issues here. One, Python has a global interpreter lock, so it is possible to do something in a thread that's going to hang up other threads for a while. The RP2 port doesn't have, by default, doesn't have the global interpreter lock. You can have a thread on either core. On the ESP32, as I said, threads run as free RTOS tasks on the same core that the main thread runs on. The reason for that is that the networking stack and so on runs on the other core, so it gives you a lot better performance. What I recommend to people is to use async I/O, and async I/O is pretty mature now in MicroPython, and there's a number of libraries that do a good job with it. So async I/O, it's coroutines. In MicroPython, they're based on generators, but it supports async and await, async with, context managers, async generators. There's some primitive synchronization things. Thread safe flags would be if you wanted to communicate from an interrupt handler or a thread to an async I/O task. Async IO.event and lock allow you to synchronize between async I/O tasks. And of course, we have streams, servers, and so on, and including TLS support. There's really good tutorial information from Peter Hinch, as well as some extensions. Q, I use a lot. He's got a ring buff queue, which is pretty helpful for like messaging and being able to handle input into async I/O tasks, retriggerables, switch debouncing, a variety of other things like that that I end up using. Debugging async I/O, there's AIO REPL, which if you've got async I/O tasks running, ordinarily you wouldn't have your REPL available because that's a synchronous task. But AIO REPL gives you the same goodness. AIO Prof, you can have it actually look at all your tasks and tell you how many calls there have been to each one, how much time has been spent. Also, Peter Hinch did a rather nice thing that basically you take a Raspberry Pi Pico and you connect it via UART or I2C or SPI to your target device, and it just sends basically a serial stream over that indicates when particular async I/O tasks have become active and inactive, and then you can look at that. Like in this case, this would be on a Slie, or of course you can have another Raspberry Pi Pico be a logic analyzer easily enough. But that's extremely handy. You can also have it indicate when a task takes too long. So you can say, okay, I don't want any task to take more than 100 milliseconds, and tell me if one does. How do we optimize? Well, there's two dimensions we want to optimize on. One is for speed, and one is for memory, flash, and RAM usage. For speed, MicroPython has got an extension, MicroPython.const, which allows you to have compile time constants. So instead of having to have a global, have to look up constants in a global table, the compiler will just put an immediate reference to the object directly in. So we skip that additional dictionary lookup. If you use const and you name your variable with a leading underscore, it doesn't even end up in the globals table. So you can save a little bit of memory that way too. Again, use locals instead of globals. Locals in MicroPython are just basically indexes into stack slots. They don't go through a dictionary lookup. There is the Python locals available, but basically upon first reference to a variable, it gets entered in the locals table, but really that's more there for introspection than anything else. Use pre-allocated buffers. MicroPython has some extensions that allow you to stream into a pre-allocated byte array or array.array, which is pretty handy. So you don't have to constantly churn memory for I/O buffers and that sort of thing. Avoid growing lists. Use integers, at least on the object representations that don't have floating point immediates. Memory views. If you slice a memory view, you've got another memory view. So typically what I would do is pre-allocate a byte array and then have memory views into that if I need variable size slices or variable offset pieces. Call garbage collect periodically to avoid surprisingly long delays. That would be one way to reduce jitter. There are two or three decorators that are available, depending on the port, that actually produce native code. There's the MicroPython.native, which gives you about 2 times the speed of bytecodes, but is bigger than the bytecodes. And then there's MicroPython.viper, which it's not exactly, it's kind of a subset, an extended subset of Python, which is considerably faster and allows you to do kind of raw pointer stuff if you really want to have raw pointer stuff. We do have the ability in MicroPython. I think you can turn this off. I haven't checked. But there's the mem8, mem16, and mem32 pseudo objects, which allow you to actually, given an address, get to a byte or a word or a short somewhere in machine memory. I recommend against using them unless you really need it, but I have used them before. For instance, for the continuity buzzer, I needed to get to a control register for the PWM on the RP2040 to get complementary polarity for the driver. So it's handy. On some ports, there's also an inline assembler available, and so you can take a method and rewrite it as assembly language, and that can be pretty handy. You can talk to hardware registers directly. Obviously, you don't want to do this if there's also MicroPython stuff going on that expects to use those registers. It might be kind of confusing, but in the RP2, there is a relatively new addition. There's an API for the PIO, which is their very fast I/O device, which allows you to read and write to pins at clock frequency, as well as the DMA subsystem. So the two of those together, you can do things like generate video directly from your microcontroller. Optimizing size. I mentioned QSTRs you just have one copy of these strings. So if you use names that are below 10 characters, they will end up as QSTRs, which are faster, both faster at runtime and also don't require allocated memory. If you freeze your modules, you can run them from flash so you don't use RAM for them. Use const. Again, precompile. byte arrays are arrays instead of lists or queues, integers, so on. So, as I said, much faster in development, especially for low volume projects. Frequently, the cost of firmware development, when amortized over the number of units, is going to be in excess of the cost of the hardware. So very often from a business point of view, it makes sense to use MicroPython and maybe spend a few cents more on hardware if you need more memory. My experience has been that it's not a big difference, especially since some of the more modern microprocessors, the MIMX-RT, the RP2040, the ESP32 all have external flash. Flash is cheap. Some of them also allow external RAM, either SPI or other. So, yeah, consider weighing development time and aggravation versus hardware cost. So, questions? I know I went through that pretty fast. Yeah.
I have two questions. So one of them is how much, of like modern Python features can you actually use as part of MicroPython? Like, can you do type annotations?
Do what?
Can you do type annotations?
Yes.
Can you do like return type annotations?
Yes.
Is there anything which is excluded?
Yeah. So there is a good table in the MicroPython docs, which talks about the differences between different Python versions. It's more or less MicroPython is more or less Python 3.5, but there's extensions like later async I/O, type annotations, a variety of other things. Let's see. Okay, hold on. I have to wear my glasses for this. There's also an active discussion board. So development for MicroPython happens on GitHub, and there's a discussions forum that's there. Let's see.
I missed out of your talk except this last slide, but I was just interested. Is MicroPython mostly the core Python language minus most of the libraries? Is that what
So MicroPython is actually a ground-up rewrite of Python for microcontrollers. So
what language features have you dropped? What have you
right, I'm getting to that right here. I'm going to point you to that. There's been a number of changes to the Python language since Python 3.4, 3.5. So here.
still have classes?
Oh yeah. It feels very like desktop Python. So for instance, in async I/O, you don't have futures, okay? But
Python 3.4.
yeah, 3.4, 3.5. So for each of the, so here's what's covered and what isn't. So for instance, matrix multiplication operators from 3.5, async I/O. It's got F strings. It's got so your favorite Python feature. My experience now, I'm not a super experienced desktop Python developer, but as I've been learning desktop Python and MicroPython together, I haven't noticed a huge number of differences. But if you want to take an off-the-shelf Python library, especially one that was made by somebody who just wasn't concerned about speed and space, you might want to make some changes to it. Literal string formatting, underscores. So they've kind of curated the various different changes to Python through the years and really kept the ones that have made a difference to people working on microcontrollers. Depending on what your favorite features are. Let's see. So for instance, there aren't method doc strings aren't there because why would you need them, right? But they do have assignment expression. So anyway, there's a good table. you know, what was added, what was left out. But basically, so MicroPython lib also is in three. Let's see here. MicroPython lib has three different kinds of things in it. It has the standard Python libraries that people expect as part of the Python environment. It also has MicroPython specific libraries, and then it has kind of additional libraries. Let me get over here so I can show you. I guess I can show you a live demo here. And it probably won't be readable. Let's see. So I'm connected here to the little so this is the MicroPython REPL, and you probably can't see it. Let's see if I make it bigger here. No. Command plus. I thought I did. It's ignoring me. Okay. So if you're at the REPL, you can do help or help modules and get a list of, for instance, what's built in. So as I said, I'm using a stock build in this case for this ESP32C6. So these are the modules that whoever did that board definition chose to put in there. And we have, you know, async I/O, we have ESP now, which is ESP specific, various different bin ASCII, Bluetooth, etc. You know, there's those. Now, if we go to MicroPython lib, there's a lot of libraries there. Okay, so there's the Python standard library. These in many cases are subsets, but there's a lot of them. I don't know if you can you see this? Probably not. Right? Sorry about my fumbling here. Are there any particular libraries that you would miss?
No.
Okay.
Some of the software I use still insists on Python 2.7.
Okay. Yeah.
2.10 is very
So the other thing that I was wondering is like, how much fine grained control do you get on your Is there the option to disable garbage collection and then freeze it?
Yes. Yeah. You can enable or disable garbage collection, and you can force a collection. And it is pretty sensible about, like on ESP32, there are multiple pools. Remember, it has to share with the ESP32 stuff too. But yeah, you can turn off garbage collection. You know, if you're in a tight loop that needs to do something fast, make sure you have everything pre-allocated. Don't try to allocate anything in the loop, of course. Yeah, you can turn it off, turn it back on. You know, the standard Python gc.enable, gc.disable.
And then it just goes out of the same system heap that you would use, for instance, with ESP32.
Right. Well, MicroPython takes, you know, gets memory from the ESP32, ESP IDF heap or FreeRTOS heap, right?
So I mean, I
No, it handles it at runtime, yeah.
But does it still use pip as a package manager, or do you have something?
It has own package manager, MIP instead of pip, but it doesn't know about dependencies. So you have to kind of think about what's required.
That quickly leads to issues with pip.
Well, package management and dependency management is an extremely annoying thing. Yeah. Yes.
On the CircuitPython side, I've been doing some exploration on changing the breakdown between ports and boards and how that's set up. Do you know if there's been any progress on that?
One of the things that we've seen with a large number of ESP32 boards is board variants. So there's now support for board variants in the build system. So you could have like even the stock ESP32 boards. Some of them have more or less. Some of them have octal SPI RAM, and some of them don't, and so on. So that would be a board variant. But by and large, there hasn't been any real refactoring. It's worked fairly well so far.
I know he was looking at some like fairly fundamental like build process changes for the distributions themselves that I think thought maybe might require that changing that port into a distribution.
Yeah. So one of the interesting things about the MicroPython build, if you fork it and check it back into to GitHub, is it's got a whole CI workflow that actually builds all of the ports. So you'll an hour later you'll get build messages saying that such and such port had a problem or whatever.
Sort of a follow-on to that, I guess. Another question is, do you know if there is an equivalent to CI build wheel or MPY cross or some other tool or best practices for doing library distributions that support multiple boards?
The MicroPython lib actually generates, so for those libraries that have native code in them, there have to be different versions. So they actually build different versions, and so when MIP installs a version, it would be, you would get the port-specific one. So.
A desktop Python CI build wheel is a tool set that sort of manages that for you. So you just sort of tell it, give me this set of platforms, and I'm just wondering if there's something out there outside of the distribution build process for library.
Not that I know of. Not that I know of. The effort has gone into making it work on GitHub. Yeah. And I had some suggestions about how to, because I ran into that. I had a library variant that I wanted to get out that used a little bit of somebody else's library, right? And there was no fine-grained way to do that easily. But yeah. Other questions? So I was thinking about on Sunday I could perhaps, I don't know how time in the workshop areas is being allocated. Helen said that it was a free-for-all, but it would seem that probably first come, first serve. But I would be glad to do a more in-depth workshop if there was any topic that people wanted to cover, or we could just get together at a table and be glad to show you things.
I did have one quick question.
Yeah.
Why is it that you chose, did you develop it?
Um,
Why is it that they chose not to handle dependencies?
Because there's a limited number of developers and time.
Oh.
Plus, dependencies in general.
Customer demand,
Yeah, not enough customer demand, and we don't have as complex a dependency, between these libraries. These libraries tend to be pretty, as of yet, they tend to be pretty self-contained for the most part. So, we're not trying to build. So for instance, I can describe one of the products that I'm shipping. I'm using, there's a nice async IO web server framework that looks a lot like Flask or like Ruby's Sinatra, called MicroDot. It also does template expansion, it does WebSockets and so on. So I'm using that. I'm using the, it's all built on async IO. I'm doing over-the-air update. There's some good libraries to support that on the ESP32. I'm using, of course, custom manifests and custom builds because I've got, you know, my own hardware.
And you were going to say that it is mostly self-contained, it only depends on other libraries.
Yeah, so as far as external libraries, I think I'm down to like 4 or 5 external libraries. One of them is microdot, but there's several libraries from the MicroPython lib, like the standard requests library. You know, is just part of the networking bundle that you typically get, right? So I can do HTTPS requests of, you know, cloud servers and that sort of thing. But there's some significant libraries like microdot, like the MQTT, the improved async IO MQTT library. There's also AIO BLE, which is an async IO BLE library that really makes BLE development much easier and just much easier to get along with. Questions? Yeah.
Are there any considerations for commercial usage?
It is MIT licensed. Yeah. So yeah, there's definitely people using it commercially, and there are companies, you know, shipping products with MicroPython on them. There's I think M5 Stack and PyCom, and of course Damien George's own George Robotics and others. But no, there's basically no restrictions. Of course, if you're using, you know, some arbitrary library, you know, you have to look at that, but no commercial restrictions, and they tend to be pretty responsive as far as picking up changes and reviewing changes to the library or to MicroPython itself. Adding a brand new port to mainline might be a little bit more difficult because they just don't necessarily have the development time. You know, if you can get enough people enthusiastic enough about it to do the reviews and actually, you know, work on issues. So this is actually a board that is going to be shipping in an IoT toothbrush, of all things. I can't really talk about it much, but this is, you know, running on MicroPython using an ESP32 module, controlling 4 pumps and a motor and sensors and a variety of other things. It's, you know, and it was I found it to be a pretty comfortable development experience overall. So, yep. Yeah.
What is the testing like that you use? Like test out of the box or something similar, or what are you using for unit testing?
There's a kind of a stripped down version of unit test, but yeah, I just use straight unit test. So I have, you know,
Separate test modules that just, you know, run on the host, right? You know, so I suppose you could run unit tests on the device itself if you wanted to, you know, if you really needed to, but I haven't found a huge benefit from it. Typically, if there's significant program logic, it's not touching the hardware directly anyway, and it's pretty easy to test on the host. I recommend that as a best practice anyway, you know, even if you're developing in C, you know, just try to do as much host testing as you can. Thank you very much.